Hi, this is a video that will help fill in some of the lecture notes that we didn't get to in class last week. The goal of this video is to learn how to use some numerical values and prefixes to write metric equalities. I suggest you use the printable lecture notes from class while you're watching. In the metric system and international system of units, prefixes attached to units will change their sizes by factors of 10. Here's a table that shows the metric and international system prefixes for large numbers, such as giga, mega, and kilo. There are also prefixes for small values like centi, milli, micro, and nano.
I'd like to show you how to use this table. Let's start with the definition of milli. Milli always gets a lowercase m in front of whatever unit you're using, so it could be milligrams or milliliters. The word milli means 0.001 of that thing, or, since you've learned scientific notation, 10 to the minus 3 of that thing. The definitions over here on the right allow us to determine the equivalency, or what equals what. So in this particular case, a millisecond is equal to 10 to the minus 3 seconds. We can also multiply both sides of this equation by 1,000. And we can say that 1 second then is equal to 1 times 10 to the 3 milliseconds. For this class, we're not going to have to worry about memorizing the different conversion factors, like what milli means or what nano means. The important part for this class is for students to be able to use these metric prefixes and the numbers to be able to convert one unit to another. So our next learning goal is to write conversion factors for different units that describe the same quantity. We're going to start with 60 minutes equals 1 hour. Now this value could be something that you would see in the previous metric table, like those little conversion factors or equalities we saw on the right side of those tables. Writing the equality as a ratio or a numerator-denominator fraction will allow us to use those equalities in calculations. So we can write 60 minutes over 1 hour or 1 hour over 60 minutes. Both are equally valid. Note that these conversion factors are read as 60 minutes per 1 hour, or 1 hour per 60 minutes, where the per means divide. I'm going to show you now how to go through some metric equalities as conversion factors. We'll start with meter to centimeter. Remember from the table that a centimeter is equal to 0.01 of a meter. I can write the equality in two different ways. Either 1 centimeter equals 0.01 meter, or 1 centimeter equals 1 times 10 to the 2 meters. I can then write that as a numerator-denominator fraction that we could then use in calculations. I can do the same thing with grams and kilograms, where the kilogram is used for large masses. Going to that table, I can see that kilo means 1,000, so I can write the equality as follows. Now that I have the equalities in terms of 1 kilogram equals 1,000 grams, or 1 times 10 to the third grams, I can then write those as ratios, where the numerator and denominator fractions are top and bottom. There I have the numerator-denominator fractions of kilogram per 1,000 grams, or 10 to the third grams per 1 kilogram. I can do milliliters to liters, and then watts to gigawatts. You can see I've chosen to use 1 times 10 to the 9th watts per gigawatt, because it's much easier to write that number in scientific notation. It's not required though. You could also write out 1 billion watts per gigawatt. Now I'd like you to pause the video and work on the next 3 problems on your own. Once you've finished, restart the video and see if you got them right. It's okay if you go back and look at the tables that are in your lecture notes so you can see what the prefixes mean in terms of numerical values. Hopefully you've done this work on your own after pausing the video. I'll show you the solutions next. Here I've written both the equalities and the various conversion factors that you could write for each of these 3 different conversions. Now, of course, each of these could be written in scientific notation or regular numerical notation. Either one is fine. Our next learning goal is to use conversion factors to change from one unit to another, like from liters to milliliters. Here's a little guide for how to do that. First, we'll state the given and needed quantities. Then maybe you can make a plan, maybe it's even in your head or written down, to convert one unit to the next. We can use the equalities and conversion factors like we just did, and then write up the problem so that we cancel some units and calculate the answer. Here's our first problem of converting volume measurements, which will be from 55.5 milliliters to liters. We're given 55.5 milliliters, and we need liters. So we need a plan to convert milliliters to liters in some way or another. The equivalency is something we just worked on. We can then write out the 55.5 milliliters, write in our conversion factor of 0.001 liters per 1 milliliter. Once we do the math in our calculator, that works out to be 0.0555 liters. One way to remember how things are going is that there's a big unit and a small number on the top, and a small unit and large number on the bottom. The big unit is the liter, because a liter is much bigger than a milliliter. And the small number is 0.001, because 0.001 is smaller than 1. The other thing we can do is see that the units cancel out to give us the unit that we want left in the numerator. We can see that milliliters in the numerator and milliliters in the denominator cancel out as they reduce to 1, and we're left with units of liters. Here are 3 sample problems to work on. The first one's not in your lecture notes, but it's a good challenge anyway. Please pause the video, work on the problems, and then restart the video to see if you got them right. Here's the solution to the first one, taking 0.00342 meters and converting to centimeters. Notice how the units of meter cancel out because it's in numerator and denominator, reduces to 1, and disappears. For the next problem, you might need 2 conversion factors because, to be honest, I don't know how many minutes are in a single day. But I do know 2 different conversion factors that relate minutes and hours and days to each other. The 2 fairly easy conversion factors, the hours per day and minutes per hour, that we can solve this problem without too much stress. For the next problem, the speed of a runner in meters per second, I suggest you start with writing the kilometers over the minutes in numerator-denominator style, and then convert one set of units, kilometers to meters, let's say, and then do the other one. It doesn't really matter which order you go in. Pause the video, see if you can get it right. Here's my solution, and I even showed you how the units of kilometers and minutes reduce to 1 and cancel out, leaving us with units of meters per second. Our next challenge, or learning goal, is to look at density. We'll learn how to calculate densities of substances and use the density to calculate mass or volume of a certain sample of a substance. It's important to know that density is constant for any amount of substance. So if you have a huge amount of water or a small amount of water, it doesn't really matter. The density is always going to be the same. Densities are usually written in grams per cubic centimeter or grams per milliliter. The formula for calculating density is that the density equals the mass of the substance divided by the volume of the substance. Here's a table of densities of common substances. You can see that the density of liquids we're familiar with, like olive oil, water, and milk, are all about 1 gram per milliliter. Things that float, like corks or ice, have a lower density, and things that sink, like silver, lead, or gold, would have a higher density than water. Here's a little map for calculating density. The important parts are knowing the mass in grams and volume in milliliters or cubic centimeters. Here's an example problem where we're given the mass in grams and the volume in cubic centimeters of a piece of osmium, which is a really dense metal. It has pretty weird chemical properties, and it's fairly toxic too. Fortunately, it's not very common. We can calculate the density by setting up a little density equation, where density is going to be equal to the mass divided by the volume. That works out to be 22.5 grams per cubic centimeter. In an advanced chemistry class, we learn about something called significant figures, which is shown as 3SF below. We're not going to worry about that for this class. In order to determine the density of an object in the lab, we could take that piece of metal, let's say, measure its mass on a balance. In this case, the piece of metal that we're measuring the mass of is zinc. And then we can put that piece of metal in a colored fluid and measure the difference in volume in the colored fluid. In this case, we know the fluid changes from 35.5 milliliters to 45.0 milliliters. We can then calculate the density. Pause the video, calculate the density on your own, and then check back in to see if you got it right. Here's the answer. All we have to do is divide the mass by the volume and come up with 7.2 grams per milliliter. We could also consider this 7.2 grams per cubic centimeter because those two volume measurements are exactly the same. Because density is a ratio, we can also use it as a conversion factor. It's really important to use as a conversion factor when we come across problems like wanting to know what the mass is of a certain volume of a solution if we know its density. For example, if the density of milk is 1.04 grams per milliliter, we can calculate the mass in grams of milk in 0.2 liters. To do that, we can take the 0.2 liters and convert it to milliliters. Good thing we learned that already in this video. And then we can multiply by the density in terms of grams per milliliter and learn that the 0.2 liters of milk would be equal to 208 grams. There's another way to write that out. I'll show you in just a moment. I prefer writing the equation out this way. It's easier for everyone to see that liters reduce to 1 and cancel out, and milliliters reduce to 1 and cancel out. This is what it looks like when using numerator-denominator fractions and canceling out all the units. It's a much preferred method, in my opinion. Our next problem has to do with the density of gold. If we know the density of gold is 19.3 grams per milliliter, we can calculate the volume of a certain mass of gold. In this case, we need to use the density upside down or inverted, kind of like we did with some of the metric equivalencies. We also need to convert kilograms to grams. Again, something that we've learned already in this video. If we start with the mass, kind of like how we started with the volume in the previous problem, we can then use the density as a conversion factor. It always makes a lot more sense to start the problem with the measured value rather than a ratio. Here you can see the two ways to solve the problem. The one in red that's written out is the one I would prefer, where we start with the measured value and then clearly identify our conversion factors as numerator-denominator type fractions, rather than the slash fractions. It's just easier to see the units that way. That's the end of this lesson for Unit 3. I hope you've learned something about converting metric units, using prefixes, and using density as a conversion factor.